Yes, it's the physics video lecture once again. Physics 4B video lecture 15. So we've been working on potential, electric potential, potential energy, and we have a really interesting application of this. It's going to take us into circuit elements, but for the moment, we're not really doing circuits yet. But it's the concept of capacitance. So let's just write that down and define it and have a look at what's going on here. Capacitance. Okay. So we've already seen that we can have one object charged with plus Q and one object charged with minus Q. So we can have, say, two conductors, they're separated and they're charged with equal and opposite charges. So that's what we're going to look at. So I'll just draw some random conductor, got a wire coming off one side, here's another one. And what we do is we charge them up, plus Q and minus Q. Well, they're not so symmetrically shaped, so we don't know exactly what the field is, although we know that there's a field pointing from plus to minus. Okay, we know that much. And then the question is, what is the potential difference between these two charged objects here? And what makes sense is that the potential will be proportional to the amount of charge. So if I have Q and minus Q, I'll have some potential V. And then if I double Q minus Q, I'll have twice the potential. Okay. So that's going to bring us to our definition of the capacitance. And so I'll just put a couple words here. Potential difference is proportional to the charge. Okay, so here we have two charged conductors. Okay, two charged conductors. Potential difference is proportional to the charge. And then we can go ahead and get our definition here. To charge, which is to say Q is proportional to V. And what we're missing is a proportionality constant, or Q is equal to C times V, and this is the capacitance. I also often write, so I'll just put this as a note, Q equals C delta V. So I use the V and the delta V interchangeably depending upon the specific situation there. So let's go ahead and just take this. Right, V is also the symbol for volt as well as potential. But yeah, let's go ahead and take that as our definition. And this capacitance, this proportionality constant, depends on the geometry here. Okay, so right now I can't say any more about it. If I take a specific shape of conductors and configuration, then I'll be able to actually calculate it. Okay. So what about the units? We put that right under here. Units, so units of C, we always do this right away. Units of Q divided by V. Well, Q has the unit of the coulomb. Again, we could be confused with that C, but we're talking about coulomb over, I'll write it out, over volt. That's C over V. But what is that? That gets its own name. It's called the farad, in honor of Faraday. Coulomb per volt. And I'll just note something else here. Typically for some circuit element that we're looking at, the capacitance will be in the microfarad. So 1 farad is an enormous capacitance in practical terms. So practically, C is often on the order of 10 to the minus 6 farads. So when you're actually doing certain problems, you'll often be coming up with something like that. Good, so that's the definition of the capacitance. To make it concrete, we'll immediately talk about a couple of examples. So the first example is capacitance of an isolated charged sphere. Okay, so imagine we have a sphere of radius r, it's got Q on it. Sphere R, and yeah, where's the other charge? The idea is that we could have a spherical shell surrounding this thing with a minus charge, except that we're letting that go out to infinity. Okay. So the outer shell is outer shell at infinity. Okay, that's why it's not there. But the capacitance, this is the easiest one to determine. So we'll start with that. And what we have here is the capacitance is Q divided by V. This time we need the expressions. There's the charge on it. What about the potential? Remember, the potential is Q over 4 pi epsilon naught R. So the Q's cancel, and we're just left with 4 pi epsilon naught R. And I'll even remind you guys, V for the point charge, we can either do Q over 4 pi epsilon naught R, or electrical constant Q over R, right? We use those interchangeably, but when we were doing Gauss's law, certain fields, we're using the 4 pi epsilon naught. So we have that here. So that's our first example, capacitance of that sphere. The next example is really the practical one we're going to use again and again. So this one we have to analyze thoroughly. And it's the so-called parallel plate capacitor. Erase here, I'll draw a picture. So now we're going to look at parallel plates. So parallel conducting plates charged, and let's see, we draw them like, how do I draw these two? Yeah, here's my profile, here's my, there we go. There you get the idea. Those are parallel conducting plates. We could have plus Q on the left side and minus Q on the right side. And I don't remember if we set up parallel plates before in our work. What we did set up was the field of an infinite plane, okay? And it was constant, and it was directed away from the positive charge. So let's go ahead and build up our discussion here based on that. So we got parallel conducting plates. We've got plus Q on one side, minus Q on the other. We got another color here. I'm going to show that, you know, the field inside the plates, between the two plates, points from left to right, or you know, from plus to minus, and it's uniform. And if the separation distance is small compared to the size of the plates, then there are very few edge effects, and in fact, there's no field outside with the exception of these edge effects. And since I'm not sure if we did that before, we're going to discuss it right now. So yeah, let's do this systematically. So we start with an infinite plane, infinite, does it have to be infinite? Just a large plane conductor. You know, the idealization is that it's infinite and that you're close to it. But here's the thing, and this will be a side view. So we're just looking at it on edge. This is the one that has the positive charge on it. And so the fields are pointing away like this. Those are the electric fields pointing away perpendicular to the plate. And we had E was equal to sigma over 2 epsilon naught, where sigma was the surface charge density. So that's an old result we had. Now the interesting thing is, if you take another infinite plate and put it here, this has the minus q, you see this field, actually I should have, start over again. So this field, this E field, in the sense of a large plate, extends all the way out here. It exists out here with the same constant value. And to the left, it exists way out here. So when we take our second plate, and again, this is close together compared to the extent of these things, and we have here fields like this. Oh no. It's got the minus charge, so the field is towards the plate. Okay. Then what happens is this. Pick this up. What happens is these two clearly add. So the sigma over 2 epsilon naught plus sigma over 2 epsilon naught is just equal to sigma over epsilon naught. Okay? They just add, but the field out here, this one, this arrow adds to this field because this is on the left side of that plate. So these two are equal and opposite and add to 0. Same thing on the right side. This one adds to that one and they add up to 0. So the result is that there's no field outside and there's, you know, that twice the field inside. Okay. So, you know, if I were to number these, you know, I'm not going to number them. I'm just going to say that this vector here this is the same vector here, they add to 0. Similar argument on the outside. So really, field E equals sigma over epsilon naught. Inside, E equals 0 outside the capacitor, and edge effects are negligible. Okay. 3, neglect edge effects. You know, edge effects would look something like this. So it would be something like that at the edges. Okay. We'll neglect them if separation distance D, let's go ahead and write it here. And this is area A. If D is much less than the square root of that area A. Okay. Much less than the side of the square. Much less. Okay, so now we have that, we can come back to the capacitance of this thing. this is the justification of, and these were individuals when we added them, right? We get two, the justification for that picture. Okay, let's get the capacitance of this thing. Okay, let's see. So we have, I think I have everything. Actually, let me even add a little to this example while we're on that subject. So I'm going to add another note. So this is now called the parallel plate capacitor. And it's so generic that it supplies the symbol for a capacitor. As soon as we start doing circuit diagrams, we're going to have a battery here, and that's going to be its voltage, and this will be the positive and the negative side of a battery. And we'll hook it up to a capacitor, which will have this symbol here. Parallel plates, and the letter C for whatever the magnitude of its capacitance is. And you'll have the plus side here, and you'll end up with the positive Q on the right side and the negative charge on the left side. So those are the circuit elements. Now let's ask about the capacitance here. We have E is equal to sigma over epsilon naught. So V, magnitude at least, is equal to, I'm not going to worry about the direction, is E times D. Okay. And is E times D. So now we have our C is equal to Q divided by V is equal to Q E times D Q, but what is that field? The field is sigma over epsilon naught. So sigma over epsilon naught times D. Finally, that sigma is Q per area, right? Surface charge density, charge per area. So we have Q over A epsilon naught, and the D is still here. So finally they cancel. C is equal to epsilon naught A divided by D. Good. So yeah, this is of fundamental importance. We're going to use this again and again. Okay, that's the capacitance. And you can see if you have a large surface area and a small separation distance, you can have a relatively large capacitance, just in terms of the geometry here. So actually getting a little ahead of ourselves, but that's okay. If you can fill a dielectric, right, a non-conducting substance between these plates, then you can avoid them touching each other. And in that case, you can make a capacitor by taking two, say, I'll just mention this. You can take a capacitor by, say, having sheets of aluminum foil separated by a piece of paper. Okay. So you've got the sheet of aluminum foil, big area, paper's really thin, right? So area is large, D is small. Of course, what do you want to do with this large surface? You just roll it up and put it in the can, and then made it very compact. Okay, so I'll just write that as a practical example. As you can see, that's what you want. You want a large surface area. It's kind of a principal thing. Large surface area, small separation. That geometrically is what gives you large capacitance. So the practical example, you have foil, and then a sheet of paper, and then more foil. I don't know what that looks like from a distance, but hearing it is everything, right? Foil, paper, and foil. Put some leads on it, and then roll it up. And in fact, if you ever cut open a capacitor, a little cylindrical capacitor, so roll it up and put it in a can. So a little capacitor that looks like this with a couple leads on it that you can hook up to a battery and charge it. If you saw it or cut it open and look inside, you'll see it really is made up of rolled up structure. Okay, so principally it uses this parallel plate idea and then makes it compact in here. Okay, so where are we going next with this? Okay, since I mentioned this cylindrical example, I'm going to go to the coaxial capacitor and a spherical one that I'll put on your homework, which is pretty interesting as well. So from the parallel conducting plates, and we saw we can roll them up, we'll just go to a coaxial cylindrical capacitor. And they also play a big role, so it's a useful example. So cylindrical, so the next example, cylindrical, this one doesn't maximize surface area, by the way. Gives an interesting example though. Coaxial capacitor. So this is an end view. So we just have radius A, radius B, and some length L. So inner radius A, outer radius B, length L. So we're going to do the same thing we did here with the parallel plates. We have to find the electric field, and then we have to find the potential, and then we have to go ahead and, find the capacitance. So the electric field inside we learned this when we were doing Gauss's law. Just pointing away, that was a symmetry argument. And we had that from Gauss. I'll even redo that calculation. So from Gauss we had integral E dot n hat d area is equal to Q enclosed over epsilon naught. And then, so we're in between, and then for A less than R less than B, we'll have a Gaussian surface in here, and we'll just have E times 2 pi R L, and the enclosed charge will be a linear charge density lambda times L. So the L's canceled on this one, and E was equal to lambda over 2 pi epsilon naught R. So I think we had that expression before, but there we have it again. Now, what's the potential? Get rid of this. So the potential is just minus the integral straight along the field, so no problem there. So the line integral, we're going to get our v is equal to minus integral e dr from a to b. We'll have the lambda over 2 pi epsilon naught, and then the integral of the dr over r, that's the natural logarithm. Let's go ahead and write it out. A to b dr over r. We have minus lambda 2 pi epsilon naught natural log of b divided by a. Yeah, and now we can take our definition again. Now, from Q equals CV, C is equal to Q divided by V. Now what do we have here? We don't have a Q explicitly, but we have a lambda, and the length of this whole thing is L. So we actually do have lambda L divided by where's my power? Pardon me, lambda. Oh, that's good. So lambda L divided by lambda over 2 pi epsilon naught natural log of b over a. I'm just doing the magnitude, by the way, so I just got rid of the minus sign. Okay, just take the magnitude. So I wanted to make sure I didn't have that extra L there. Okay, so this cancels, lambda cancels. The capacitance is going to be 2 pi epsilon naught L over natural log b over a. And that makes complete sense, so we're satisfied with that. Because it's just scaling with the length, okay? So twice as much length, twice as much capacitance of your coaxial cable. And then natural log of b over a. Now, I don't know if we're going to do it on this one. There's an interesting case here, namely, suppose A and B are very close together. Then you've got that thing I had just been talking about before, where you wrap something around in a cylinder. So you should be able to expand this or find a limit such that if A is just slightly less than B, you regain the parallel plate formula. Okay, so that would be an interesting one to look at. I'm not sure if it's in the homework or not. We are going to do it on the spherical example, though. So yeah, it'll work. It'll work. Okay, so that was the example for the cylindrical coaxial capacitor. Ended up here. And you see these examples give very good practice with the field and potential concepts as well. So the next one is for the homework. I think I'll discuss it right now. Consult the clock first of all. Good, good, good. So next example is the spherical version of this. So instead of a cylinder, you do the same thing for spheres, and you get an analogous result, okay? So they're both good problems. So next, concentric spheres. and I'll just write here, homework. I'll assign that at the end of the hour. But you just have to look back at this one to see how it was done, and you do it for concentric spheres. The field for the spheres, let me draw the picture. So for the spheres, it's really the same picture with the side view, except it's not a cylinder anymore, but we know we can use Gauss's law again, or we can actually just use the point charge formalisms. Same idea, radius A, radius B, but now they're spheres instead of cylinders. Great problem. And some good applications also in the homework. So, what are we going to do next here? I think we go to a discussion of energy. Yeah, these are all really great principal issues now. So if we go back to the idea of the capacitor, I had these separated charges, plus and minus. Now we can think of it as follows. There's a positive and a negative charge. They're attracted to each other. So for me to separate charge requires work. If I had two charges, positive and negative, I have to work to separate them. And if I can store that separated charge, I've stored work, which is to say there's potential energy stored. Charge separation represents stored potential energy. So that's our next topic here. And that has something to do with the capacitance as well. So yeah, we'll return to just the basic idea of separated charge. You notice all of these examples have had separated charges. Plus Q on one side, minus Q on the other. So returning to the original definition, in fact, maybe I'll draw my little cartoon again. Right, here's the plus Q, here's the minus Q. Charge separation. Represents stored work. Stored work, of course, is just potential energy. So if we think of our parallel plates, example, and if they start out neutral and then so begin neutral, uncharged, and then we'll take plus Q over to here, plus Q, which means we'll be left with minus Q over there. Separate a little bit of charge. Then that, am I using W or U? I'm using the letter W, fine. So dW is going to be V dQ and remember I had Q equals CV. So I have Q over C, so I have Q over C dQ. So that's my first increment of work that I've done. This is by the very definition of energy and potential, right? Potential was energy divided by charge. And now I've taken my definition of capacitance. I've got Q over C. I'm using a lowercase q because we're going to integrate it up. So this expression is when bringing dq over to one side, so to speak. So my little q's here were dq's, okay. Good. So now we can integrate this. And what do we have here? We have integral Q over C dQ, and we're starting out neutral and we're ending up with the whole thing loaded up with a charge Q. And that integral, of course, pull the 1 over C out, Q dQ is going to be Q squared over 2. So that integral is W equals 1 over 2C Q squared. So let me just write it Q squared over 2C. Q squared over 2C. Make sure you see how that integral goes. It's a basic one, obviously. Okay. And we can also plug this definition in, and then we could have 1 over 2C C times V, the quantity squared, and then C squared cancels C, the denominator, so we end up with 1/2 C V squared. So either of these. So I'll just put them in a box. So there's the stored energy, Q squared over 2C, for W equals C V squared over 2. And in this case, you know, V or delta V, depending upon how you set things up. Okay. That's that, you know, the voltage difference. Sometimes we write delta V across there, or we just use V. Okay, so that's the energy stored in the capacitor. And by the way, this was not restricted to this configuration. This is just the one we're using, okay, to illustrate it. Because this really was just based on the increment, the definition of potential, and then the definition of capacitance. So that's the energy stored in a capacitor here in red. So yeah, just to make sure, energy stored in a capacitor. And that's how much work it took to store it, you know, to charge it up, and that's how much energy is stored there. Gotta consult the clock once more. Yeah. So my last discussion topic for the hour, and maybe we'll look at some homework problems, is kind of an interesting principle one. Now we can go back to this parallel plate capacitor, because we're going to ask, where is the energy stored? Remember, this is a form of potential energy. The idea is we can get it back again, and you know, later on in the semester we definitely will be getting this energy back again. Okay, so where is the energy stored? Where is the energy in a, or where is it located? Where is the energy in a capacitor located? Question mark. Right, we're thinking of this now as a potential energy. I'm gonna, yes, actually that was why I was, let's go ahead and do this. We're going to change the letter to U, capital U, for potential energy. Okay. That's why I was thinking about that. And that way, when I say energy stored in a capacitor, I can say parenthetically, this is potential energy. Potential energy. And the question is now, where is it stored? Where is it located? So yeah, we're just going to analyze this picture again. This will generalize too, but the parallel plates are good for this type of situation. So here we have the plus Q, minus Q, and we have these E fields that we know all about. That's the nice thing about the parallel plate capacitor. It's a constant E field, uniform. It couldn't be better. Okay. We know what's going on there. So, where is the energy located? So for the parallel plate capacitor, so here we have potential energy. We're going to use the second form, capital U, 1/2 C V squared. Okay. So what was the capacitance of the parallel plate capacitor? That was just epsilon naught A divided by D. So that's what I'm plugging in right there. And the field, or the potential, was just the electric field times the separation distance, and we're squaring that. Okay, so there's the capacitance parallel plate capacitor, E times D squared. Let's go ahead and label this thing just so we know that we have D right there. And we're just going to simplify this, or U is equal to 1/2 epsilon naught, and then we have A times 1 power of D, because D squared over D has 1 power of D. So we'll put that in parentheses, A times D, and then we have E squared. And this example is really good because we know there's only E field between those plates. This is a volume. In fact, this is the volume between the plates. Area times separation is the volume. So what we can do is define an energy density. So if this is an energy, if we divide by volume, we have energy density. So what we're going to do is take a lowercase u sub E, that is equal to U over volume. Yeah, I'm going to write it out simply because there are too many V's here. And that leaves us with 1/2 epsilon naught E squared. And this is general. The potential energy is stored in the field. So the field takes on a lot more reality in electricity than it has in gravity. You know, I'm even going to make a little note about gravity here. So yeah, this is important. This is the energy density, okay? Energy density. If this was, joules, this was energy, this is joules per meter cubed, energy per volume. Okay, so lowercase u sub E, 1/2 epsilon naught E squared, the square of the electric field. So that leads to really great problems because say the electric field isn't constant, then can we prove that the energy of the charged capacitor, which is just one of these formulas here, yeah, in particular this one, can we get that if we were to integrate one of those fields, say inside the spherical capacitor or the cylindrical one? Okay. I think one of our problems is going to ask us to do that. I'll check that before we go. Okay. So the energy density, energy is stored in the field. So let me put a couple more words down on this. Stored in the field. You compare that to what we learned about gravity last semester. In gravity, I'll just put this as a note. You wouldn't even ask this question. With gravity, we say potential energy, say, is mgy. Okay? Mgy plus constant. Suppose we have something, we have a mass here on the top of a cliff of height h. Okay. We can't, we're not even led to the idea that the potential energy is stored somewhere in the air here or in that height difference. So in gravity, we don't make that claim. But here in electricity, we clearly see the energy could be thought of as being stored in the field. And we're going to go places with that because eventually electromagnetic waves, energy will be stored in the field as well and transmit. Okay, I think that's, let me consult the clock again. So yeah, this was just parenthetical. Let's just check out what we had for the homework assignment. I'll write them down and then I'll have another look in the book, see what I was thinking. So this is the homework, we'll call it homework 15. We're in another chapter of the text, chapter 24. And I have written down here 17, 18 problems, 17, 18, 41 ABC, 41 A, B, and C, 49 and 50. So let me see what was going on with these. Okay, 17 and 18. Yeah, these are just, 17 and 18 are just, 17 is just using the definition. 18 is kind of interesting. So 17, just the definition, some solve for some unknown. For 18, we're talking about a couple of spheres that are separated. So now I think we have spheres of radius r. Yeah, plus q and minus q. But here the idea is that the separation distance L, which I'll just call it L here, separation distance L is much greater than the radius. And what the reason we have to specify that if we want to get the capacitance of this, and it'll be an estimate, because we have to be able to treat these things like point charges. Okay? In other words, in reality, if they're too close together, they're going to affect the charge distribution. But we're going to say they're far enough apart so we can treat the charge distribution as being uniform. So I'll write that here. L much greater than R, so that charge distribution is uniform. And then there's no problem, it's easy. Is uniform. Okay. Good problem. So that's 18. What do we have here? 41 A, B, and C. Yeah, just numbers. Parallel plate capacitor. Not sure what I thought was so good about this. Oh yeah, it asks about the energy. So 41 A, B, and C is also just the numbers. No big deal. So what about 49 and 50? I think those are the good ones. We can even do 48. So 49 and 50 are both those spherical capacitors that I was discussing, and you're going to work your way through the problem just like our cylinders, except it's a spherical geometry. And yeah, there's a lot. These are great. These are good problems. And I'll probably work them, especially if people ask me to discuss them next week. So these two are both spherical shells, all kinds of interesting stuff to do right there. Good, and with that, I'll leave you and see you next time.